All right, we can do our Kirchhoff law now. There's two of them. There's a voltage law, which is today's star, and then there's another one called the current law. Kirchhoff's voltage law, Kirchhoff's current law. Today we'll just look at the voltage law. And the basic idea of it actually is I think intuitive. Well, maybe not the way it's stated here. Here it says around any closed loop, the total change in voltage is zero. So voltage can go up, voltage can go down, voltage can go up, voltage can go down, and every time you cross some kind of a circuit element, the voltage either goes up or down. And what this is saying is that if you get back to where you started, like let's say you started here and you started walking this way and your voltage went down and your voltage, went down and your voltage came back up. Well, by the time you get back to here, the total change is zero. You're exactly back to where you started. Now, the reason I say this is intuitive is you can think of it this way. You can't walk to school and home uphill both ways. Although when I was a kid, I had to do it. I had to do it through 2 feet of snow with bare feet. I had to walk to school and home uphill both ways. Okay, you know that's not true. So you can't do it, right? So, I mean, here's your house. Here's the school. Maybe the school's a little higher than your house, and maybe you take a real path that takes you up this hill, and then you come back down, and then you get to the school. And even if you take a different way home through the valley or whatever, if you come back to where you were, you're at the same height that you started with, the same altitude, the same elevation, whatever you want to call it. It's the coming back to where you started is what makes this law work. So if you go back to where you started, you can't go to school uphill and come home uphill both ways. You can't do it. And in a circuit, you can't just keep increasing the voltage. You can't just increasing the voltage is like pumping up the pressure. And you can't just keep pumping up the pressure every time you go around. You pump up the pressure more, because it's going to explode. It doesn't work that way. It doesn't work that way. All the pressure that goes up is matched by all the pressure that goes down, the same way that going uphill is matched by going downhill. Okay, that's the idea. That's the principle. That's the physical idea. What we're going to do, of course, is we're going to apply Kirchhoff's voltage law to doing some mathematical analysis of circuits. So I'm starting with, this is a nice circuit, right? And I'm actually going to do the same circuit twice here. I'm going to do it two different ways. I'm going to do it the simplified way that you may have learned already in one of your electrical courses. There's a simplified way to do this one. And then I'm going to show you the general analysis. And the nice thing about the general analysis is it always works, always. The simplified analysis will work for this particular situation only. And yeah, it's shorter, so it's nice to know. But the general analysis works always. And since we want to build up our ability to analyze any circuit, we've got this, we've got this general analysis to learn. But before we get to that, let's do the special case. First of all, I should label some of this stuff. Maybe I should call this, I don't know. Let's call this a 24-volt battery. So, by the way, that's the symbol for battery. It's kind of like, in the old days, they used to make like, think of like plates with like acids and leads and acid, kind of a sandwich type thing. They'd call it a pile, I believe, a voltaic pile. But anyway, that's where the symbol comes from. And it's got this little plus here just to tell you that that's the positive terminal. Just like on your car, you open it up, there's a big plus on the positive terminal of your battery, right? So that's my voltage source, if you will. This is kind of like a pump, because it's the thing that's driving the flow. It's the pump. Just like if you want to drive water through some pipes, you're going to have a pump in there somewhere. And it's actually, the flow is coming out this way. It comes out the negative terminal, okay? Which is interesting, because when I was in college, it came out the positive terminal, but somebody seems to have fixed it, and now it comes out the negative terminal. Whatever. So the flow comes out the negative terminal, which makes sense, because the negative terminal is where the electrons are, and the electrons are the things that flow around, and they flow that way out the negative terminal they go. So there go the electrons. This symbol over here is for resistors. So I've got two resistors here. Doesn't it look like it would be kind of hard to go through there because it's all crooked and stuff? So that's the symbol for resistor. And you rate resistors in ohms, so I should rate these resistors, I don't know, I'm going to call this one 4 ohm resistor, and I'm going to call this one an 8 ohm resistor. Okay, so we got our 2 resistors there, and what's going on in this circuit? Well, there's the pump right there, 24 volts of electrical pressure. Boom, that's what it does. It pumps up the pressure, and then your electron stream is coming this way, and then all of a sudden, well, you have to get through that. And that's kind of like when you blow through a straw. Remember the idea of the pressure's higher in your mouth than it is outside. So as you blow through the straw, to force the flow through this crooked straw here, you lose a little bit of your pressure. And then you have some pressure left, but then you have to lose more pressure to get through this resistor, to get through that obstacle, if you will. And guess what? You're back to nothing. You're back to where you started. You've just got 0 pressure. Good thing there's a pump. Pump it back up. Pump it up. Yay! We want to pump you up. Anyway, and then you lose some pressure, and so on. So it keeps going like that in a cycle. So let's actually write that out. Voltage rises. Oh, I gotta learn to write a little more neatly with this thing. Voltage rises as you cross the battery, and I'm talking about crossing it with the flow. In other words, if you're Ant-Man and you're over here, then as you come through the battery, you're going to feel the pressure go up because you're going through a pump. It's pumping up the pressure. You feel the pressure go up. That's if you go this way. Obviously, if you're Ant-Man and you do it backwards, if you're Ant-Man and you start on the high pressure side and you go through it this way for whatever reason, you're going to actually feel the pressure go down. But let's just follow the flow, okay? And we'll follow the flow. That's what we'll do. We'll follow the flow. So as I follow the flow, the voltage rises as I come across the battery here, and then the voltage drops. Voltage drops a bit as go across this resistor. You lose some of your pressure, and then you lose the rest of your pressure because that's the last resistor here. Lose the remaining voltage pressure. Put that in like quotes. As you go across this one. So let's try to keep these 2 resistors separate here. So the pressure goes up, the pressure goes down, the pressure goes down. You're back to nothing. And that's exactly what this Kirchhoff analysis is saying. The total voltage change is 0. You go up across the battery, but then you go down, down, you're back where you started at 0. Up across the battery, down, down, you're back where you started at 0, and so on. Okay, that's the whole idea of Kirchhoff's law. Now, I wanted to analyze this circuit, and by that I mean, hey, what's the current, man? And how many volts do you have across here, and how many volts do you have across here? Well, we can solve for that. Yes, we can. We can solve for that. And the way we would solve for that is the simplified analysis is to go like this. Since it's all one loop, that's what allows us to do this simplified analysis. We can say that the total voltage, total driving voltage, maybe I should say it that way. The total driving voltage is, well, just the 24. And then we can actually add up the resistors, the total resistance. And I'm sure you've seen this somewhere before, but when you have these 2 resistors hitched up in series like this, you can just add their resistances together. So 8 and 4 is 12. So the total resistance is 12 ohms. I really should put volts here. And 12 ohms. The resistances truly do add. 4 plus 8 is 12. And so that means if I'm talking that the total voltage is 24 and the total resistance is 12, then I can get the total current. How? Ohm's law. Remember this little button? You want to solve for the current? You put your thumb over there, and you say the current is E divided by R. So in this case, I have 24 total volts. I have 12 total ohms. 24 divided by 12 is 2. I got 2 amps, man. 2 amps. Not ant-man, but amps, man. I got 2 amps, man. Well, that was nice. I got 2 amps. And then I can go a little further. I can say, well, what's the voltage from here to here, and what's the voltage from here to here? What are those two voltages? Well, resistors also follow Ohm's law. And come over here and put your thumb over the E. E equals IR. Voltage equals current times resistance. So the voltage across the 4 ohm would be, well, see, this 2 amps. This is the beauty of it. It's a nice series circuit. This is 2 amps, 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 2 amps. It's always 2 amps flowing all the way around. It has to be. It's only one pipeline. What goes in must go out. If 2 amps comes in here, 2 amps must go out for any section of pipe. If 2 amps are coming in here, 2 amps are coming out here, and so on. Anywhere you go in that pipe. And so since the current is 2 amps, and the total resistance, or no, not the total. I wanted to do the 4 ohm resistance first. So across the 4 ohm, we have 2 times 4 is 8 volts. So we've got 8 volts across that resistor. And then across the other resistor, we have the 2 amps again, but that one's an 8 ohm. 2 times 8 is 16 volts. So we've got 16 volts across this one. And did you notice, were you expecting this? 16 plus 8 equals 24. Dun, 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 dun. It has to, because that's what the Kirchhoff's voltage law is saying. What goes up must go down. It's true of voltage around any closed loop. Yeah. Yeah. Okay, so anyway, if you guys want to do your own YouTube, if you can get it to go viral, I'll give you 50 extra credit points. How's that? You have to have a song. Kirchhoff songs. Give you 500. No, give you 50. But it has to go viral. Okay. So I just did a full analysis of that circuit. Now, what did I mean by a full analysis? I solved for the current, and I solved for the voltage across each of the resistors. And I knew that this was 24 volts, so I didn't really have to solve for that one. So I solved for the current, and I solved for the voltages. And I was able to do it using the shortcut that since it's all one loop, like I was saying here, you just have to add up your total voltage, add up your total resistance. You can use Ohm's law to get your total current. It's all the same current. And bada boom, bada bing, bada bing, boom, boom. That'll work for this one. In fact, I almost hate to say it, but this simplified approach will work for all of tonight's homework problems. But if you do it that way, you're defeating the purpose of the homework. The purpose of the homework is to learn a general, and I might call this a general Kirchhoff analysis. The reason we learn the Kirchhoff analysis is not because it's longer, because, well, it is longer, but that's not why we're learning it. We're learning it because we want to be able to analyze more complex circuits, maybe circuits that have another branch in them, maybe circuits that have another branch in them, maybe circuits that have, this is called a current source. When you have current sources showing up, all shortcuts are off. All shortcuts are off. So if you want to be able to analyze more complicated circuits, what happens is there's no shortcuts you can use. So you need to have a general way of analyzing the circuit. And one of the tools we use is Kirchhoff's voltage law. And it's saying that basically around any closed loop, the total change is 0. We base it on that idea. Around any closed loop, which means if I walk around in a circle, say from here to here, if I walk around in a circle, all my voltage going up and all my voltage going down has to be 0. Okay, how's this going to work? Well, let's get started. Here's how you do it. It's kind of a few steps to it. First, draw your current. And it's okay to get it backwards. So a lot of people get stressed trying to draw their current. They don't know whether to go clockwise or counterclockwise. And it doesn't matter. It actually doesn't matter. Because if you get it backwards, your answer will be negative, and that's all. Your current will be negative. When you solve for current, you're going to say, oh, -2? -2? I must have drawn the current backwards. But that doesn't mean you have to go through and analyze the whole thing again. You just say, well, I'll just draw my arrow going the other way. Okay, so you don't really have to worry about whether you're getting it right. That said, it's usually more fun to get it right. So if you remember this idea that the current comes out the negative terminal of the battery, then I can say, okay, there goes my current. And then since I don't know how many amps it is, or I'm going to pretend I don't, I'm going to put X there. X amps. Label it X amps. Or at least put the X on there. Label it X amps. And that's the current coming out the battery. And of course, it's the same current here, it's the same current here. It's going to be the same current here. It's going to be the same current here. It's always X amps, X amps, X amps. I don't really need these arrows. But it's nice to have an arrow for every circuit element. Here's a circuit element, circuit element. We got 3 circuit elements. I got 3 arrows. It's usually how I do that. Let's see now here. Having done that, let's do another step. What I'm going to do is I'm going to put a negative, I guess I'll write out negative, where your current, and I say your current because you drew it, where your current enters any resistors. I guess I should say put negatives. Put negatives when your current enters any resistors. So in other words, here, see this current? See how you've got it drawn going up? Well, if it's drawn going up, that means the negative will go on this side. And then for this resistor, I'm going to put a negative on this side. And by default, it's positive on the other side, right? So this resistor here has a negative there and a positive there. And then this resistor here has a negative on the way in, a positive on the way out. By the way, the battery, you just trust that, the battery, they're going to put the positive stamp on there. You don't have to worry about which way the arrow goes. Don't worry about which way the arrow goes. It doesn't matter. The battery, trust the battery. The plus is there. That's the plus. The minus has to be on the other side. Okay. Now, why am I putting all these pluses and minuses on there? Well, what these will do for us is these will tell us whether the voltage is rising or falling as we walk. So remember I was talking about Ant-Man before? If Ant-Man starts here and Ant-Man walks across the battery, he's going to see a rise in volts. See the positive on the way in? Yep, that's what tells you when that it's going up. When he comes over here and he goes across this resistor, he's going to see a drop in voltage. See the negative on the way in? That'll tell you, right? We knew already this is a pump, and then you're going to, as you come across, you're getting pumped up, and as you go over here, you're getting deflated, I guess. But the reason we put the minuses and pluses on there is just to make it a little bit easier to just walk around in circles and just pick up your pluses and minuses as you go. Okay, so we'll see this in the next step. In fact, that's a good step to put in red, I reckon. Start anywhere on the wires. Walk in a loop, and then record your voltage changes as you go. You can start anywhere. Doesn't matter where you start. Well, we had Ant-Man starting over here, so why not have him start over here? And it actually doesn't matter which way you walk either. Do you hear that? You can walk with the current if you want. You can walk against the current if you want. It doesn't matter. As long as you get the pluses and minuses set up, you'll get the same, or equivalent equation anyway, either way. So I'm going to start with Ant-Man, and I'm going to walk with the current. So the first thing I see is I see positive change in voltage. And how many volts is that? Whoops. I was supposed to label that 24 volts. I was supposed to label that 8 ohms. I was supposed to label that 4 ohms. Well, now it's labeled. Okay, so here we go. I got plus, and I see 24 volts as I go across the battery. Out comes Ant-Man. Over here comes Ant-Man. Up comes Ant-Man. He sees the minus on the way into the resistor, so I put a minus. And then I need to write the voltage change, right? The 4 is not the voltage change. The 4 is ohms. That's a resistance. The X is not a voltage either. The X is current. But remember from Ohm's law, you can take resistance times current. So we've got, well, actually you can write it this way too. We've got a resistance of 4 ohms. We've got a current of, don't know, X. And so actually I can use 4X to stand for the voltage drop across that resistor. There goes Ant-Man. He's out the other side. Now he's coming across a minus as he enters. So you grab the sign on the way in. You know, you don't grab the sign on the way out. Grab it on the way in. I'm coming into this resistor. I see a minus on the way in. And the volts here, again, I have to say ohms times amps to get volts. It's Ohm's law. R times I, or I times R. Okay. Then Ant-Man is coming out the other side. And then he keeps coming, and he's back where he started. And when you get back where you started, equals 0. Equals 0 when back to start. There. Now, once you've done this a few times, this really isn't that hard. You're just walking around in a circle, picking up your pluses and minuses as you go, picking up your voltages as you go. And just remember, if it's a resistor, you have to take ohms times the current to get your voltage. And look what we got here. We got ourselves a nice little equation we can solve. If you solve this equation, first you get the two like terms together. A minus 4x and a minus 8x is a minus 12x. And what you might want to do here is add 12x to both sides. And then since it's 12x, I'd want to divide both sides by, not x, but by 12. And guess what? We're getting x equals 2 amps. Remember, x is the current. 2 amps, just like we got the easy way. Just like we got the easy way. 2 amps. And then if you want, you can come back over here and say, well, that voltage then is 2 times 4 ohms is 8 volts, and this one's 16 volts, and so on. But there, I have shown you the method. I'm calling it the long way. It is longer. I mean, this was shorter, right? What's the total volts? What's the total ohms? Boom, I got the total current. That's pretty short. Unfortunately, it only works for this situation where you have a nice little loop like that and no complications. If you have complications, you need to learn a general method. And we practiced the general method on the easy case just so you can see that it's working. And it did. It worked. It gave us the same 2 amps. So I'm going to end with this other example here. And I think what I'm going to have to do is I'm going to have to try to get this sort of out of the way here. Maybe I can do this, right? That sort of works. Okay. What's this? This is a nice circuit. It's got some resistors, resistor. It's got a battery over here. This says 120 volts, and you see the G. G must stand for something. That's a generator. And then this is what's called an internal resistance. In other words, inside the generator, you've got 0.22 ohms of internal resistance. We often ignore that when we're doing, I mean, this is 349.22. I guess that's not ohms. But anyway, 34.22. We often ignore the internal resistance. But if you want to be careful, you can take it into account. So actually, while we're here at the generator, let's do this. Often what you do is you take that 0.22 ohms, which is a resistor, and technically the resistor is, again, it's inside the generator, but we can just we could just move it over here, especially since it's all the same branch, right? It's all the same branch. So I'm just going to move it over there. There, that's a good idea. So take your internal resistance, move it over. That's a 120 volt generator now. Resistor, resistor, volter. Okay. Let's follow our, looks like a 4-step plan, just to get used to this method. Step 1, draw the current all the way around. And since it's unknown, we're going to label it as X. Well, which way is the current going? Is it going clockwise or counterclockwise? Doesn't matter. If you want, just put an arrow down. Just pick a way. But I usually like to guess it. Now, if you look at this battery, remember the juice comes out the negative terminal, so that battery makes it want to go that way. But if you look at the generator, there's its positive, so it wants the juice to go this way. So we seem to have a little bit of a push-a-war. So which way is it going to go then? Well, if you look at how strong the pushers are, that's a 120 versus 9. Guess who's going to win? The 120 is going to win. So I think we can safely say the current's going to go that way. X amps, that way. X amps. Down she comes, X amps. Here she goes, X amps. All the way around, X amps. Draw your current all the way around. It's X amps all the way around. This is a good habit because sometimes we'll have circuits with branches and it won't be X everywhere. So here it's X everywhere. So anyway, for every circuit element, you want to clearly indicate what's my current through that circuit element. I drew the current. It's unknown. I label it X amps. Step 1, complete. Step 2, put a negative wherever the current enters a resistor. So here's a resistor. Put the negative where the arrow enters. Notice I'm only looking at the arrow I drew. Don't look at this. Don't look at this. Don't look at this. Don't look at this. Don't look over here. Don't look over there. Don't look over here. Don't look anywhere else. Look at the arrow that you drew on that resistor. We drew the arrow going that way. So it's entering here, which means I put the negative on that entry side. Okay? Don't look anywhere else. Put your blinders on. Just focus on the resistor itself. I see the current coming in, so the minus goes there. End of story. Coming up to this resistor. Well, I'm focusing only on that resistor. I see the current coming in the bottom, so that's where the minus goes. End of story. Now the generator is a different kind of beast because they put the positive on there, and when they do, that's a permanent kind of a feature. So the negative will be here. Here's another resistor, looking only at the resistor. I don't care about the generator. I don't care about the battery. I don't care. Looking only at the arrow I drew. The arrow is coming in on this side. So that's where I put my minus, that's where I put my plus. And that's it. And then this is not a resistor, this is a battery. So the battery already has the plus on it, and you just trust it. Put the minus there. Now what you might be thinking is, hey, I thought current was supposed to come out. I thought current was, come on you. I thought current was supposed to come out the negative terminal. Isn't it supposed to go this way? And the answer is no. It would if it was all by itself, but it's got this 120 volt thing pushing against it. So you can force flow against the normal direction of a battery. And by the way, that's called charging the battery. Anyway, that's step 2. I put all my negatives and positives, really. Step 3, pick a spot on the wires. This is my favorite part. Pick a spot on the wires. Doesn't matter where you start. Doesn't matter where you start. I'm going to have Ant-Man, really he's a capital A, isn't he? I'm going to have Ant-Man start here, and I'm going to have him walk with the flow. And again, I don't have to. You can walk against the flow. You get the same, or you get the same answers in the end. You really do. So you pick a spot on the wires, start walking in a loop, recording the rises and falls of voltage as you go. And you got to remember this. Across the resistor, you do resistance times current. Okay. So if I'm starting here, I see a plus on the way in. So I write a plus. Now what's the volts is the question. In this case, they're telling me the volts. It's 120 volts. Put the 120 volts there because that's the volts. I come out. Okay, I'm coming to another circuit element over here. I see a minus on the way in the door. So I put a minus here. And what's the volts? Okay, 0.22 is the ohms. That's not the volts. X is the amps. That's not the volts. But if you multiply those two, if you multiply 0.22 times x, you get volts. Okay, so it's kind of like where's the beef, except it's what's the volts. Ant-Man comes out this way. Okay, we see a minus on the way in. Minus again. What's the volts? 9 volts. So I'm not multiplying 9x or anything weird like that here because the volts is 9. So I put the 9 there. 9. There we go, 9 volts. Ant-Man pops out the other side. He's coming this way, coming this way, coming this way, coming this way. Sees a minus on the way in. Put the minus. What's the volts? Well, since it's ohms and amps, you have to multiply those to get volts, 4x volts. He comes out this way and comes up there. Oh, minus on the way in. What's the volts? Well, that's ohms, that's amps. Multiply them, 3x gives you the volts. Ant-Man pops out the other side. He's back to where he started. Equals 0 because he's back where he started. That's done, and I guess it says here, when you get back to where you started, finish your equation by writing equals 0. I suppose I could have made that part of step 3, but the real step 4 is now we solve. So this is the fun part. Time to solve. Let's see now here. Looks like everything's on the left side of the equation. So some stuff equals 0. You want to put like terms together. There's no parentheses, don't have to worry about that. But I want to put like terms together. So here's my two constant terms, or numbers. A positive 120, take away 9 is a positive 111. And then the rest of these are x terms. Negative, negative, they're all negative. If they're all negative, they add up to a big giant negative. Looks like negative 7.22x. 4, 5, 6, 7, yep, they're all negative. 7.22x equals 0. I can add that on both sides like this. Did you see that? What I did was I added 7.22x on this side, and I added 7.22x on this side. Remember, the equals is where the wall is. So you're left with 111 on the left is all that's left on the left, 7.22x on the right. Finally, it's time to do your dividing. Make sure you're looking at the x. What we need is 7.22 on the bottom in order to get the x alone. And so the x is going to be, take the 111, which is on top, divided by the 7.22, which is on the bottom, and that'll get us our amps, especially if we can find our calculator. Woo. Come on, I know I have one. Where'd you put it? Oh, for heavens. There it is. I got my calculator. I'm going to push buttons. 111 divided by 7.22 is, our survey says, 15.37, and remember, x is the amps. 15.37 amps. That's like a big yay moment. You've got your current. On the other hand, we're not really done. Yes, it's 15.37 amps and it's the same everywhere, but we don't have all the voltages. So we have this table down here to help us summarize our answers. So the current through everything is 15.37 amps, right? So it was the same current all the way around the circuit. So I can just put arrows like this. It's always the same current. Now across the 120 volt generator is 120 volts. And across the 9 volt battery is 9 volts. That's how those work. That's what a 9 volt battery does. It forces 9 volts right there. That's got to be 9 volts no matter what. And that's also what the generator does. If it's a 120 volt generator, it's forcing 120 volts right there. So you don't have to do anything weird for those. But for these are resistors. So if you want the voltage, you have to multiply the current times the resistance. This is the current. Right, this is the voltage we're trying to get. And these are the resistances. So you have to multiply like that resistance times that current, that resistance times that current, that resistance times that current. So 3 times the 15.37, we got about, what now? This is like 46.11 volts. And then we got the 4 times the 15.37 is 61.9 0.48 volts. And then we got the 0.22 times the 15.37 gives us the 3.38 volts. And then we have fully analyzed that circuit using Kirchhoff's voltage law. Cool. So I invite you to do the same thing. Use this as your template for all three of the homework problems. Okay? Follow those steps in that order and you'll get used to it. And by the way, you can always check your answers quickly by saying, well, the total volts is this and the total ohms is this, so I know the current must be this. You can always check your answer that way. But again, try to follow this method of walking in circles because we're going to need it. We're going to need it.